So, hello everyone, and welcome to today's reading group. Today we have Jiatong Shi. He is a PhD candidate in the Language Technology Institute at CMU, advised by Dr. Shinji Tabe. His research focuses on speech representation learning and its application across various speech processing tasks. And today he's going to talk about singing voice synthesis, data curation, modeling, and evaluation. The stage is all yours.
Yeah, thank you so much for the introduction, Pune, and also thank you so much for the invitation as well. So it's really glad to present here. So mostly we'll be talking about, as already mentioned, it's mostly about the synonym word synthesis. So talking about me, I'm a fourth year, a PhD candidate now, and mostly working on speech representation learning. So maybe you guys will be thinking about why I'm presenting the synonym word synthesis. I'm actually more in the person want to explore more in the way of how we can expand the application to the method that we have studied in the speech. So I would say more like Singing Voice is more some side project I'm working now, but it's continued to growing in recent years, to be getting to some of the very interesting works. So I'm glad we have the space here to share with you guys. So we just get started with we'll be mostly talking about several works from the collaboration from Renmin University of China, and also at the same time we have been doing some additional works in terms of from the data curation and modeling and also the evaluation as well. So we'll be going with mostly with this outline. So talking about synonym word synthesis, it's more like a very straightforward concept, especially in recent years, and there's many actually related works coming up. So mostly trying to utilize the music score, which could be referenced as the melody and the lyrics to synthesize the voice. And we're it's quite simple in general, but it actually contains many of the detailed information, especially if you consider how the format of the music scores will begin with. So, for example, for this one, we'll be considering more like a music note and also the lyrics and also the duration, where the lyrics is mostly is different from the, for example, usual text to speech layout that we actually do not have any control to the duration by just doing the model itself to doing the inference. But usually we will have a more explicit control on the syllable level of the lyrics so that it could be matching the music notes to generate the sound. So it's actually very tricky in the case of considering how it could be compared to the text to speech. Usually we think it's a similar task, and so do many of the recent works actually applying the similar techniques. But at the same time, you need to consider some more fine-grained information from music score that to generate it. So as a result, it's actually very difficult to get the data, and also modeling will have a large change because of this kind of domain mismatch and also the additional constraint from the data format. So in general, we'll be going with more challenges in synonym voice synthesis here. First of all, it's definitely the data curation. We would definitely want more data, and also whether we can explore many of the interesting idea to be for the modeling for synonyms specifically, where we also want to have a more a better evaluation, easier evaluation other than the subjective ones and so on. So given that, we'll be firstly starting with the data curation part. And from that, we'll be introducing mostly about the work that we have been presenting in interspeech, last interspeech, mostly working on the synonym voice data scaling up. So the concept here is very straightforward. So compared to TTS, actually text to speech, it's very easy to get data somehow because we do not have any actually additional requirements when we actually recording people's voice. There are some a legal issue always, but it's actually lighter than the as well as sending voice here. Mostly it's actually will be have a stricter user guidelines. For example, we need to have some more a professional singer other than the amateur. And also we need to have more in the case of considering the copyright issues, especially for this music domain, it's very sensitive. And also at the same time, we usually need a more a professional, high quality recording environments compared to the speech. Speech, we do have similar issues, but a singing voice is even more higher requirements for the recording and so on. Whereas at the same time, maybe you guys do not really know if you have any of the experience before, to recording in the recording booth of the singing voice, you could be probably knowing that actually singing voice is actually taking longer to record compared to speech. So for example, for speech, usually we just speaks, and it's actually more easier where if we want to record a singing voice for a specific sounds, we usually need to take hours of hours for a few minutes of recording. So it's actually very time consuming if you want to really reach the high quality and so on. Whereas at the same time, if you remember, like we actually have a music score information, and the music score information somehow is very detailed in terms of like how it will be going with the duration as well. So along with like compared to text to speech, if we only need the text information, like usually the singing voice needs such like music score information and lyrics alignment and so on, which makes the annotation process very difficult. And consider that like actually one of the things that we actually recently thinking about is like what are the real world production of the singing voice going like. So if you are like getting into any of the experience into that, it's actually in the real world music production, the singing voice is not usually directly used. So like usually we'll be have some like a substantial effort like after that, like for example mostly by mixing and mastering for the from the music producer and so on. So this actually during this stage, actually there are many of the techniques it's using. For example, from like more like parametrical vocoders, digital signal processing techniques, and so on, like to change a little bit of the timbre of the voice and so on. So actually, there's actually many of the empirical usage or empirical strategies that could be using in the like process, so that it could be improving the singing quality and also even helping it to be using for the further like usage and so on. Whereas like considering that, like can we use this concept to like in the production of like a kind of music signal or like to do the singing voice refinement to have a better singing voice data generation and preparation, especially for the singing voice synthesis purpose. So here, like we then like elaborating our ideas in the like contribution of this work mostly by trying to introduce a unique data curation method for the new singing voice synthesis data, and also release two large-scale multi-singer as well as corpora compared to the existing ones. And we also like demonstrate the use case because it's actually from more like artificial like strategies over the tuning of the singing voice data. So like we actually want to demonstrate that this method, even after this manual tuning process, we can actually get it to be real application using in the different scenarios of the singing voice synthesis. So going with more like maybe we can start with the curation process, which is more like detailed in how it could be going with. So it's more like it consists of 4 stages. So firstly, we'll be going with the data preparation, whereas this process will be going with like typically singing voice synthesis data, existing singing voice data. Like this could be mostly related to the information such as the music note, the melody information, duration information, and also how it's kind of aligned the lyrics and the melody itself. So given that we'll be continuing with like the information verification and correction. And this is actually through an portal of the existing like a neural synthesizer called like ACE Singer, which actually provide an interface that people can interact with voice so that they can understand how the layout of the voice is and also how it can be further refined. So to give you a brief review of how it will be going with like the whole setup is like they will have the interface like this one. It's actually very similar to many of the professional music production to like for example the Logic Pro and maybe Cubase. If you are interested in music production, you must be heard of these two toolkits. Like so, actually, it's very similar. So they will be have the whole like MIDI ground for people to play with, and there will be have many of the different interface so that they can be adjust, for example, the length of the note, music note, and also adjust the difference of how it will be going like with the music score and so on. Whereas at the same time, they could be also helping with the edits of the lyrics, so that they could be changing the lyrics on corresponding side, so that they could be make sure that it's aligned and so on. And given that after we have this information, it's like a most important thing that will happening here is like we do not want to trust only the neural synthesizer. Otherwise, we are just like a distillation process, like going with the existing synthesizer. So what we did next is mostly trying to giving the existing voice, and we do some manual tuning by trying to match the voice between the original singing voice and also the new singing voice that we generated. So it's more like an iterative process to match the synthesized singing to the original like singing voice, and where we'll be have many of the key steps here. Like for example, the fundamental frequency contour modification and adding a breath sound before and after, or like a giving it like a rhythm, and also to adjust the vibrato and so on. And furthermore, we'll be potentially considering like fine-tuning the syllable duration to make the singing voice more natural. So just to give you also like some examples here, like this is a pitch control that you can draw from the singing voice like synthesizer here, which mostly trying to tune the voice, though they're generating from the existing music score, but then they are trying to add more human effort into the medium point so that you can easily add more control to the voice with the parametrical vocoders and to improve the like more naturalness from the like a listener's perspective. Whereas given this, like we will be continue with the singer adaptation. That means that we will be have multiple singer to be generating with the same neural synthesizer. But at the same time, we want to filter out some of the like unnatural singing phrases because like mostly it's very natural to think about like not all singer can be proficient in all singing phrases. So like if there is out of their vocal range, we'll be probably removing this sound like just to keep the better quality data from the process. And after this curation process, we will be get some resulting data set. So we're starting from the OpenCPAL, which is one of the most widely used like a singing voice data, which is also widely used in my following works like discussion and so on. And it's actually sourced from the OpenCPAL, and then we actually trying to convert the OpenCPAL voice into different singers, and also involve this like curation process to improve the singing voice like quality compared to the original like neural synthesizer directly. Whereas then we also continue to like expand another data set from Kissing, which is additional new sounds, like which is actually a little bit more difficult compared to the OpenCPAL, where it's like previous one is more focusing on one public domain, where like focusing on the Chinese pop music, where this one is more like in the multi-genre and also have a high melisma effect, where the melisma here is like means that we have one singing like syllables and contains multiple music notes to be singing at the same time. Whereas given this, like we actually compare a little bit of the existing data set. So at the time when we're releasing it, we are actually the largest data for the singing voice synthesis. You might be surprising that actually why we are having so small size of the data for singing voice, but that's the reality. So it's very difficult to get the data for singing voice synthesis. But this kind of process actually largely expanded like the singing voice synthesis scope so that we can be using for various purposes and so on. And also like compared to the cases that where some of the licenses a little bit restricted, we try to make it as better as possible. So like making it to be CC&C there, but like that's the best effort we can try at the time. Yeah. So given that, like we given this data set, we further tested in the different scenarios. As I mentioned, like actually this data set is originally sourcing from a neural synthesizer from a commercial system. So it's actually a little bit difficult, like to see, like some people will be saying, oh, this is still a synthesized data, but how it can be using for the synthesis purpose, like because this you still want to using this data to train a new synthesizer. Is that a distillation purpose only, and so on? So actually, we're trying to see like how this data will be helping with different scenarios of the data. For example, by directly training the singing voice synthesis from the corpora, and also trying to, for example, conduct some transfer learning, use this pre-trained model as an initializer, and also like for to testing on other data set. We're also testing in the scenario, for example, for the joint training purpose, like by simply combine this data with the existing data to test if this will be have improvements and so on. So in this way, we actually have a few of the experimental setup from the direct singing voice synthesis. We directly conduct to two analysis with the two data set, where we'll be going with like transfer learning in the case of how it could be transferred from the in-domain scenario and out of domain scenario, and also the joint training scenario with the like SAE kissing plus kissing. So there's actually a few of the details. So probably you want to look at paper for more, but mostly we are working on two systems. Like the one is more like a cascade system with like the only the model that from the firstly converted to multi-spectrum and then use a vocoder to reconstruct it. And whereas we also have the way singer tool method where it's a more like an end-to-end scenario where it's directly generated the sound from the music score. And all the implementation, by the way, is based on the ESNet, so it's all open source there as well. So given that we also test a few of the evaluation metrics, I think you probably will be seeing this metrics all the time later with the following works as well. So mostly it's more about some of the objective evaluation metrics together with the subjective one from the mean opinion score and so on. So given that, like we firstly test on the direct SVS, and it's explicitly show that actually by using this data set generated, if you compare with the JT here, it's actually the ACE singer data, and the source JT is actually the same type set with the original OpenCPUB data. So it's actually showing that we actually have a very comparable performance over the modeling of it. So like it's actually have very similar performance. So maybe I can show some example here so that you can hear how the voice will be going like. So this is actually the one that we doing after the manual tuning with our like proposed procedures. So, and the other one is the source, so which is actually the ground truth, which is the natural singing from the OpenCPUB originally. So they are actually quite like comparable, I would say. Like for at least from my ear is actually somehow it's like the mostly like they're adapting the singing style to another singer, but they still keep the very high quality in terms of like how it will be generated. It's actually verified in the mode score, like when people are evaluating it, like it's actually reaching very similar performance in the case. So it's suggesting that the data could be very cool in terms of like directly using even comparable to the ground truth after this manual tuning process. Whereas at the same time, it could be measuring like how the recent proposed, like for example, synthesizer will be, though artificial, is actually could be potentially like get a better mode score compared to the existing cinema synthesis data. So even though there are like a quite so sophisticated method so far with the VI Singer 2, but there's still a very large gap between our like source data from the GT here, like the ground truth from the ACE keying and the current cinema synthesis system. So that it means that there's actually still a large gap. So even though maybe we are not exactly matching the ground truth, like a source ground truth from the original singing OpenCPUB, but still like this is a very good standard here, like for people to approaching with the data and so on. Where at the same time, like this similar finding is kind of verified with the OpenCPUB, which is more data there and also more versions and so on. So like actually showing that it's actually comparable and also more like a stable process that could be using. And with that, like we actually continue with the transfer learning scenarios, like where for the in-domain scenario, like this pre-training will be benefits both like the models here, whereas in the out-of-domain scenario, like it will be also observed like more like subjective evaluation benefits from this like using the model and so on. It's actually testing in the from the original pre-trained is like in the Chinese voice, when here is testing the Japanese voice. So like it's totally quite different sound level and so on, but it's still like showing very good performance in terms of naturalness improvements. Whereas the last one is also could be using as a multi-singer augmentation. So where we're actually testing in the combining with the original data set of the casing, and so that trying to see if we combine the data, whether this will be helpful. And by testing this, like we'll be starting with some voice example here as well. So and it's actually perfectly recover the melisma effect that showing in the like singing voice synthesis. But let me play the sound first, like hear what we'll begin with that. 我就去哪里耶 So you can hear it from the original singing voice synthesizer, like the last part of the voice where there's a multiple note in a single syllable. It's actually very difficult because this phenomenon is very unique in singing voice synthesis, and it's actually not so many works can be easily attached to that because of especially consider the transition. And this one is actually especially a bad case that even is like not working at the last few notes. Whereas given that we're going with the other one with the synthesizer. 我就去哪里耶 So especially for the last part, if you're focusing on that, it's actually get a great improvement. However, there's still a bit of like the improvement space compared to the ground truth if you hear the ground truth. 我就去哪里耶 So it's still a small gap there, but at least it's much improvements from the original like a synthesizer we are training on the original data. So like this kind of improvements could be largely due to the data improvements like here because it's all the control, we can control the experiment and so on. So it's like very impressive and also really like kind of making the key thing to be working for this end-to-end system. Before that, it's actually not working so well. So to summarize of this kind of a brief like section here is like we actually released two large-scale sending voice corpora and also like showing case of this kind of unique like data curation process that could be helping with the data generation with the existing data. So with this way, we actually could be helping escape some of the copyright issue that from the, for example, collecting the data from the other singers and so on. We're just expanding from the existing data. Once we get approval from the existing data, the people who released the existing data, and we actually could be further continue this study. And also like we also showcase this could be also helping in many of the scenarios, even though it's originally from a neural synthesizer, but after this manual tuning, we actually could be involving many of the improvements of how it could combine with the existing corpora and so on. So just to briefly thank you, like mostly for many of the like people, like mostly from the two source, like one is like the ACE Studio, like they are supporting our research as well, and also like the OpenCPOP releaser from NetEase is also helping with this release of the data, so that we can make sure the license is not the issue here. Cool. And continue with that, we will be going more on the modeling section, where we'll be discussing two works that will be going with the discrete-based SVS and so on. So I think one thing that we got started with, like we want to have there are actually a very new trend in the signal generation in general, like audio generation, music generation, speech generation, and also singing generation. Here is like mostly going with like the way of how we're going with the going to the discrete representation in the middle. So there's actually many of the discussion here. So I will be briefly summarizing why we are kind of moving to this direction. So one of the things that is kind of helping with the scaling up. Before that, we actually only can do a very small proportion of the data for the training, especially for example, for the conversational TTS. Usually at the time, like usually we frequently see the model is training on, for example, liberal speech with ATK and so on. It's more like to be a very high quality data though, but still like they need to be limited to be 6 hour, less than 60, 600 hour and so on. So that's actually very difficult at the time. And we actually difficult to scaling it up because like once we introduce some noise, the data will be very noisy and making the training not very stable and so on. Whereas like at the time, like when the YOE first came out, like I think it's one of the very pioneer works, like they started to going with a discrete representation, where it shows that they can be usable for the large scale training with this kind of discrete representation and making it working. So it's very impressive at the time. Where later on, like there's also many of the discussion here. For example, it could be further improve the storage efficiency, where like compared to the raw waveform and also the self-supervised representation and also the acoustic features and so on, we actually could be compress the data a lot. And if we only use this information, we could be training the data, training some model that comparable to the existing SOTA. So it's very impressive. So that making it also a good choice to go with a discrete representation. Where later on, there's also like showing some enhancement in the like commutation. For example, by considering the same time, like, actually they will be training more faster with the case of using the discrete representation, which is also makes sense because like will be more in the case of how the discrete representation is making into the system, so that it's kind of a compressed representation allow compressed information allow, so making the training much faster, and even the inference will be much lighter in the case. Sorry, and the last one is actually will be also helping with the multimodal connection. So it's very trivial nowadays because there are recently so many speech language model coming up. So given this like various of the like modeling like insights here, so we're actually trying to see if we can expand the discrete representation for the synonym synthesis as well. So this is mostly like a collaboration with Renmin University of China and also the Tencent, mostly focusing on using the discrete tokens for the synonym synthesis. So here, like, it's actually, though we actually have discussed lots of like benefits from using the discrete representation, here when we're using in the synonym synthesis, there are actually lots of like issues happening. Mostly it's like, first of all, it's like the acoustic details is very difficult to like keep with the synonym synthesis, especially when we have a very high standard of the information that we want to keep with the synonym synthesis. We need to have very high quality data there. And also we want to have a high demand for the melody flow. So like, it's not like in speech, mostly we care about naturalness, but in synonym synthesis, more than that, we need to care about how the melody flow is like accurate and or like consistent and so on. So I would say like the tolerance of the speech versus sending. Like usually people will be more tolerant a little bit bad speech. It's okay, but like if the sending voice have some like a distortion in the middle of the melody, that will be a disaster. So by talking about that, like we actually propose this like a toxin framework, mostly by trying to exemplify like a procedure that could be tackling how this like system with a discrete representation will be helping with the sending voice synthesis. And so we'll be talking mostly with two questions. So first of all, where the tokens are extracted from and how the tokens are formulated and so on. So going with that, we firstly talking about like this, like where the token is extracted from. So there's actually two choices on our hand. Like one is semantic token and acoustic token, where the semantic will be more from the self-supervised learning model, where the acoustic will be more from the neural codec model and so on. And for the better like construction quality, we then like actually when we tested a few of the scenarios, though the acoustic token show is seems to be having a better reconstruction quality, but then when we tested it in our scenario, we found like it's actually not adapt well to the sending voice synthesis. Where actually, if we go in with the semantic, it's actually easier to train the vocoder with that. Compared to given this scenario, we actually then choose to use the semantic token, which also trying to like limit the size of the training, make it easier because like actually, if you remember previously in previous section, actually the training data for the sending voice is very limited. It's not that large. So if we want to scale it up, like maybe acoustic will be one choice, but like here, the semantics is the only choice that we can make at the time, like to make it working. So in that case, like we actually further expanded into the way of how the MMM is working on. So like to briefly mention how it's going with is actually we're trying to formulate into the multi-stream scenario instead of only the single stream from a single layer. So as a result, we could be considered, for example, a single model from different layers and different models from different layers, and also a single model from the same layers, but then doing iterative clustering over that with a residual-based clustering, similar to the RVQ style, but like more on the classical method, like we directly comprise the semantic information. So by considering these options, we actually could be formulating a three formulation here. And then we actually trying to decide which one will be the best. And we firstly started with a weighted sum strategy, and then trying to identify the highest weight over that and choose the top two or top three in the case, so that where we could be still limiting the size of the code books, but then helping with the full entire modeling, so that we ensure that the whole training is possible. So given that we actually test a few of the formulations like from like different models, well, remember the formulation one is on the different the same model with different layers, and the formulation two is from different models, and the last one is like the same model but same layers but with more iterative like fine tuning over that. And where we find like it actually will be more dilemma like between like the vocoder and the acoustic modeling. So vocoder is just to resynthesize the voice, where the acoustic modeling is to combine with the sending voice synthesizer. So at the time, we found like it will be first of all, it's actually effective for both of the vocoder and acoustic to improve with the three strategies. Where like they when they combine, it could be even get better performance in the case. So here, like we actually then choose to combine all the three techniques that we mentioned here, like to hopefully to be improving it in a more better way of how it will be going with a single like discrete representation for the sending voice synthesis. And another one, as we remember, is like the melody issue. Like if we want to enhance the melody, we mostly want to alleviate the melody degradation with a more enhancement module. So specifically for that, we actually designed this kind of melody predictor and melody enhancer to improve the performance. And to get more details, we actually firstly like trying to integrate a more predicted like a melody in the middle, so that we could be have a detailed like fundamental frequency prediction at the time, where it could be utilized for the vocoder training at the following. So it's which also shows that it will be improve the performance a lot. Whereas later on, this kind of combining this melody information, and a very interesting factor here is coming up is like this predicted F0 could be also using for the vocoder. So as a result, it's some here like mentioning here like the vocoder become the new bottleneck when we directly synthesize the discrete representation from the self-supervised learning model. So here we actually trying to add more information here. Like the straightforward idea is to adding the predicted fundamental frequency from the model, and which is helping a lot as well. So by combining this, like we actually achieving the better performance by using the full setup and also make it possible for the final generation. So this is more like in the detailed discussion. So if we go into the general table like this, looking like this, so we firstly mostly testing with the system that using the existing mouse spectrum and also the latent variable, which will be mostly depends on the way I think like a system where we'll be going with the way E that so that the latent information is restored in the way of like a latent representation. Whereas we also compare it with the discrete token representation. So while we do have the lower bit rate because of our implementation with like the discrete token, we actually could be improving it a lot from the subjective evaluation and also the other like objective metrics from this like mean capture distortion from like fundamental frequency correlation and so on, and also the mean opinion score as well. So given that, we actually find a very interesting thing as well. Like it's actually already reveled in some of the previous works, but at the same time, we also verified in the TTS like synthesized corpora scenario is that by using this experimentation, we could have a high convergence speed. So since we do not have the bandwidth to conduct the subjective evaluation, we just simply test the male capture distortion, where it's a more like objective evaluation that we can get handy. At the time, like we found like by just considering the training epochs, if we use the mass spectrum-based method, like by predicting this, doing the regression here, it actually will be take a much longer time to predict or to make it more stable at the last. Whereas if we just change to the discrete token, the prediction will be easier. Like the classification will be better, faster than the regression, and as a result, it actually could be converging much faster at the time. So we will be make it to be converge as a more like a halfway compared to the mass spectrum-based model. And compare with that, so we will be sharing some of the examples that will be going with the token and how it will be going like with the whole system. So we'll be maybe we'll consider time will be just play one example here, but feel free to chat more in the case of since we already released the pre-trained model and you are free to like doing some inference as well. Wow, yeah. So we're starting with maybe the last one in the case. 小酒窝长睫毛，迷人的我可就要。So this one is the ground truth. And this one is the baseline. And note that this baseline is not the one that we are from the mass spectrum, but also from the single discrete unit. This is the reason that we want to show that how much improvements that were made actually to make the token to be working. So just to show the case, yeah. 小酒窝长睫毛，女人把我可就要。So as you can hear from here, so the voice is almost distorted at the time. So this is the first time when we're training the system with a single layer discrimination just to copy the existing speech framework to the sending voice synthesis. It's actually not working. But after we applied all the techniques that we mentioned before, it's actually improved a lot. So let me see this one. 小酒窝长睫毛，迷人的我可就要。So as you can see here, like it's mostly like getting recovered, but still like there's just some improvements, further like room for improvements. But at the same time, it's already much better than the baseline, which is the first time when we applying the disparate token for the SOS. So to have some take-home messages here, we firstly propose this kind of discrete-based SOS system, where we trying to go with some melody enhancement by integrating the melody control and also improve the acoustic prediction time. Also, this kind of a token like formulator or like more in the way of like doing applying the MM framework will be helping a lot. Where at the same time, it will be also helping with a lower storage cost and high convergence speed at the time, which make the development to be very fast. And also the all the code and pre-trained model are released in the pull request. It's still not merged because of the CI test, but we will be trying to merge it soon. Yeah. So later one is that we actually further continue this additional study. It's actually a parallel study, but we actually which we're trying to improve the discrete token from this single voice synthesis. The previous one is more on the way that we trying to going with directly apply the speech representation or discrete representation from the speech pre-trained model to the single voice synthesis. Whereas this one is trying to directly improve the discrete token, like trying to how we can incorporate more information that could be adapting to the single voice synthesis. So the question here is like we have the focusing and it presents a practical solution for the existing speech software reasoning model. But at the same time, like can we kind of acquire some of the more like a discrimination for sending voice specifically, like more like to be adapted to the domain that we are want to showcase of the how the performance will be going with that. So it's like the potential issue here with discrete SOS. So the easy way, I would say, if we have more data, is we just train a self-reasoning model with single voice, right? Like it's very straightforward, but it's very difficult because we do not have enough data, and it's very difficult to acquire this data because of the license issue, as we mentioned before. So as a result, like we actually trying to still want to use the speech self-reasoning model, but how we can adapt it to the sending will be a very important question, and also how it could be going with the discrete representation. So there are indeed some domain mismatch in the speech compared to the sending voice. Like for example, there's will be more like nuance like pitch variations for sure, and also like more like the vocal range will be quite different, and also like in the case of the duration will be quite flexible because sometimes we'll be sending for a long note, but like when we're doing the speech, we'll be lucky not to do that, right? So, and the last one is actually it's also more like a fixed resolution, and it seems to be suboptimal from one of my previous like active works. So we discussed about the multi-resolution information. So it's actually could be possible to be using for the multi-resolution information for this purposes again as well. So given that we trying to fix all the issues or like to mitigate all the issues or combining all the challenges, here we observed to a new framework named like SynOMD to train a new discrete tokens for sending voice, like so that could be applied to this kind of specific sending voice synthesis or like a more in the way of how to representing sending voice in the discrete representation scale. So the overall scheme of the system is looking like this one. So it's actually will be still have the self-reasoning model here and have a resampling model and a vocoder here. We'll be expand the module one by one here. So firstly, we'll be going with extract the features from the self-reasoning model. As we mentioned before, there's no speech sending voice self-supervised learning model here already. So what we did here is trying to extract it from the frozen pre-trained speech self-supervised model, which is the easy option that we could be handled at the time. And also, like it will be adopt many of the knowledge from the existing speech self-supervised learning model for the for the improvements of the following components and so on. Whereas then we trying to attach with the problem that the domain gap between this speech and sending while using the speech self-reasoning model directly. So what we did here is like trying to transfer the speech features to sending features by additional like transfer encoder that which could be helping with like adapting the information flow to the sending voice synthesis. Whereas going with the following one is more on the like a fixed representation issue that we're trying to adapt a more like a multi-resolution issue where we're trying to incorporating this like multi-resolution features in a UNet-based resampling module so that we could be firstly downsample it and upsample it so that make sure that information is still contained in the case, but also making the whole system to be like working well together as to consider different representation. Where lastly, we then to resynthesize the waveform from this all the information that we combined with hidden representation, so that make sure that it can be adapted to directly to the sending voice synthesis. So note that this framework is definitely still unsupervised, so we actually do not need any of the supervision data. It's more just the waveform, and that's enough. And then with by considering the whole scope, we are trying to adapt the representation in the middle so that it could be linking to the sending voice synthesis more tightly and by attaching the different problem that we mentioned here before. So given that, like we mostly attaching this information, and then the following steps is actually very trivial. Like we actually adopt the similar concept as what we did in the speech set, where we just applying some clustering method in the for the intermediate representation and using it for the following application and so on. So for example, for one of the example here is like we show for starting with the 20 millisecond one, we're doing more like multi-resolution style modeling so that we could have like the 80 millisecond representation, 40 millisecond representation, and 20 millisecond representation and so on. Cool. And given that we're firstly pre-training this scene OMD on a combination of data, including the ACE OpenCPOP, because it's the largest one that we could get at the time, and also like M4 Singer, OpenCPOP, and OpenSinger, which are all like the same domain, but mostly focusing on the singing voice. Whereas later on, like we started with the Hilbert base, which is a very naive model compared to the previous one that we tried. Previous one mostly going with the XLSR and VivoM large, but this one is very base model, and we still want to show how it could be improved with the scenario. Where then we test two scenarios. One is like on the singing resynthesis that's more related to the vocoder task. We're giving the representation whether we can resynthesize the voice. Whereas later on, we're going with singing voice synthesis by trying to test how the performance will be going with that. So this will be the full table of the whole like the resilience experiments, and they sound more like complicated here. So we'll be going this like more in the details. But mostly we are trying to see like compared to the one that with the single representation, we could improve a lot by using this like OMD framework that or like to adapt this discrete token into the framework that we have been proposing. And it's also showing like many different aspects, for example, combining the way of like multi-resolution and also combining the way of like the adaptation from the sending data. It's also all the information could be helping a lot with the modeling here. And just to note that here, we actually do not use the F0 information. It's actually compared to the token that we use F0, which improve a lot. But this one, we actually want to mostly focusing on the performance of the discrete token. So we actually removed F0. So like making the result a little bit bad at the start, but then like by using this unique techniques that we adapted to the singing voice, actually could we recover this information efficiently and make it possible. And the later one is also we testing in the SVS scenario, like where we further testing in the scenario with the discrete-based SVS. It's a little bit different from the token that we actually do not have the melody enhancer at the time. So mostly trying to attach the experiments with the existing discrete token, which makes the baseline very bad. But at the same time, we could be improving a lot with this OMD. And so we just hear two ways of the male spectrum generated sound and also the discrete sing OMD here. 在一起找梦，分开了交通。And this is the discrete singing OMD. So I would say like there already like there's still some mismatch. I would say it's not comparable to the mouse spectrum, but it's actually improved a lot when we're adding the F0 information to that. But at the same time, it's actually got already a lot of improvements from the data that we get from if we go using a single like a discrete representation there directly from the speech self-reasoning model. And if you're interested in the more of the demos, actually we will have more information in this webpage, and you could be seeing like how it were largely improved from the original like voice from the discrete representation from the speech. Cool. And given that, like I would say, mostly the take-home message here is like we propose this SYNOMD, which is trying to have a more like a singing oriented, but I would say it's more like generalized. Like if you want to adapt to any of the domains, this could be definitely a good strategy that could be considering like to adapting this representation from the self-referencing representation. Whereas we also demonstrate this robustness and efficiency and even the effectiveness of this SYNOMD tokens. We actually have more details in the paper, so please feel free to check that as well. And all the information is also in the parallel waveguide repo, which you could be searching publicly on the GitHub. Yeah. So the last one is like the last fun part for the evaluation side. So which will be going more extension of how the singing voice will be going with the evaluation side. So this will be briefly expand a work from the firstly the data set of the same modes and also more like exploration on the same modes prediction. So given that like the topic is here is like starting with the evaluation is hard. So before that, we can see like mostly we need to use a mode score. As it's very like time consuming. At the same time, it's also like money consuming at the time, very expensive. So like we need to like pay a lot of money and also like to handle lots of like rubrics to make sure that it's working. And it's very difficult to control all the experiments in this scenario. And we want to explore some of the techniques that we could be using for the automatic evaluation. We are starting from that. We have some existing objective evaluations, but it's very difficult to align it with the human preference. If you see in the previous table, usually they are not related, so it's very difficult. At this point, like we actually trying to see like in speech domain, we already have lots of modes predictor here. Like they're evaluating mostly from like many of the existing successfully like works from, for example, more voice most challenge and so on. And so they really like a burn like a kind of like a boom to be like many of the existing metrics and to be using for the speech side. Whereas they're already using in many of the speech like synthesis paper and also widely adopted in many of the scenarios like to be using for the model comparison, and they're actually very stable. So it's very cool. Like, do we can so the question here is coming to the synonym voice synthesis. Can we do that something about the synonym voice? So which is actually we do not have the data for that. And why not collecting the data by ourselves? So like this is a straightforward question that we could be coming with that. So like we then kind of further developing it into a more sophisticated way that we could be testing more in the comprehensive scenario of how it will be going with the data curation. So here we trying to combine all the resources that we have for the one that we could be acquired, mostly from the different data set and also from different models, and even from different settings, from like the sampling rates and also the codebook number in the codex and so on, to control different scenario that could be applying to the whole like a vividness of the data, and also make sure that it's more in a comprehensive view. And then we kind of doing this data collection, and then we'll be finally realize like a 105 system in total, where it consists of more than 6,000 sending samples. Whereas to be for reference, like actually in speech side, we have the voice most challenge 2022 release data from the previous like voice conversion challenge, and the data set is more around the size of this range is more around 7,000 samples in total. So our size is actually already comparable to the existing speech set. So talking about that, we actually conduct two versions of the data annotation, starting from 31 system and then further expanding it to 75 systems, so that making sure that it's kind of better coverage of the system. And the data of the way one is actually using in the voice most challenge 2024 as a public challenge data. So then, like further with that, we kind of are doing more like a split of data, and also make it to have a comprehensive like review. So we actually have a more intense view of how the unseen data set will be formulated. So specifically, will be even not only to mention of the existing data that we have, but also trying to have some unseen models to be reserved for the test data, so that we can make sure that it's more applicable and also generalizable to the existing like data where we want to have it out of domain information and so on. And the after we get data set, it's quite straightforward that we want to study some of the analysis. So like here we present a very simple one, but there are actually more in the paper that we have. But one of the things that mostly like the ground truth is better than the vocoder-based system, and then like better than the synonym voice conversion, better than the synonym synthesis, and better than the codec. And the reason that codec is not working well at the time, we found that it's actually we suspicious that actually most of the codec existing codec model in the public available here actually not adapt well in the synonym voice synthesis. They because they're mostly neural codec at the time. So like they actually showing that the performance in the synonym voice is still a lake. Actually, maybe because the data is so small, and maybe because the focus is so minor, there's not so many focus existing in the codec set, and so on. So which will be potentially some further extension that we could be made in the future works in the codec set and so on. But at the same time, then we test it with the baseline on the same modes. It's a very straightforward method, like from the self-supervised learning model with a linear layer to do the prediction of it. We do not make many of the iteration here. So, and here, like I think the interesting fact is that for these specific scenarios, we found actually the larger model is not better, and multilingual model is not better. Even though our data, if you remember, like in the previous layout, is really consists of most of the Chinese and Japanese data, but that's the reality for synthesis. We do not have any English data. Very like interestingly finding, and at the time like this kind of. Originally, we were thinking of a multilingual model will perform better, but actually not in the scenario when we're doing the quality prediction. And a very interesting fact, by the way, actually, we provide the baseline model with our V1 model with this simple architecture. But actually, this baseline model achieved the best performing system in the Westmost like 2024 challenge. Even though many of the other systems have been performing many of the advanced techniques, but actually, a simple method actually works well. So it's very interesting. And given that we also test on the unseen data as well, like the result is very mixed. And I would say we need more time to understand how it will be going with, but it's showing that we'll be seeing like, first of all, the multilingual is still maybe not a good choice at the time, but at the same time, like how it will be going with more balance of different scenario and different like potential of the self-reasoning model will be definitely a good question to study in the following case. And given this, like we have it's more like simple paper. So we mostly release this data set. We have the data is already open source at Hugging Face. And actually, we also released this pre-trained predictor as well, so that I can easily test the CMOS quality with a very easy front end, and so that it won't be tasted so much time. And we also have like a little bit more evaluation beyond the sitting voice, like it's a more advertisement. So we have this Versa toolkits as well at the same time. So if you're interested to try, like we actually incorporating more, it's like up to 64 metrics in the speech and audio evaluation supported currently. And a few more last slides is like mostly about more funds in the cinema voice. The community is actually looking for cinema voice a lot. Like we actually have lots of like exciting movement here as well. Like for example, for the cinema voice conversion, we have a first like cinema voice conversion challenge. It's actually also in preparing for the next cinema voice conversion challenge if you're interested in. And we started from like this collaboration with Nagoya University and Tencent, where we also have this kind of cinema voice deepfake detection challenge at SLT and Mirix. So mostly working on the to identify the anti-spoofing in speech, where extending into the cinema voice and how it could be using for the real world scenario and so on. And that's pretty much the thing that I want to discuss today. And thank you so much for attending. And yeah, and that's pretty much the thing. And thank you so much. Mm.
Thank you so much, Jiatong, for the presentation. It was very insightful, all the papers you presented. So if you guys have any questions, you can drop them in the chat or you can raise your hand to ask them directly.
Yeah, please.
Yeah, Mirko?
Thank you for the talk. Just like want to connect my question to the one of the last results you show where you show that way to VEC, like the base version, not the biggest one, right, gives the best performance for that task. Can you elaborate a little bit more? Like, what is your intuition about that?
Yeah. Actually, we have a little bit similar findings in the ML Superb at the same time, but like from this one is like we do find like given the scope of the data, the larger model could be kind of difficult in the case of like adapting to the domain mismatch. So it's like, for example, in the way of like even the XYSR, it's like though it's training, but it still like have a large base on the speech side. So in that way, like actually they will be have a more like a fixed like a pattern that will be like doing with the existing like domain information, with especially with the speech side. So actually, it turns out like the base model will be have more flexible range that we when we adapting to the domain and while keeping the information. So that's mostly the intuition we have so far. But frankly speaking, is I would say still need more investigation here. It's more like we started with a rough like a test in the case, but I would say like potentially like this could be like more like investigate in the later space, but still like at time we saw it's more in the domain mismatch issue. Yeah, always Anders.
Thank you. So just like a follow-up, actually, if you go in slide 51, right?
Yeah.
A little bit back.
Yep.
So here you said you take the layer 6 and 33. So why specifically this, right?
Yeah, it's a good point. So the strategy here is like we're firstly doing a weighted sum of all the layers for the training for the vocoder training, and then we select the highest weight one with noted here like the weight is all learnable. So then we at the next step we then select the weight with the highest like value at the time as our following experiments, because we want to reduce the layer of like code at the time, because we were going with the 24 layers, so too much. So at the time, so we trying to doing some learning based strategies to do that. But frankly speaking, there's many recent works, right, like coming up in speech set, like showing that this weighted sum is not the weights from the weighted sum is not very valuable, or like sometimes it's wrong in the case. So like it's also worth interesting scenario of how to test it, whether it will be still true in the sending voice domain as well. But at the time, like that's the easiest way that we could be getting some of the intuition of which layer will be performing well. So like so we then conduct that strategy at the time. Yeah.
Thank you.
Thanks for the question. Yes, please.
Pune also has a question.
Yeah, thank you, Jiatong. It's like very interesting. So one thing is like for the semantic, so basically you use this SSL model and then train the vocoder based on that. So I assume that music should work with a higher sampling rate compared to a speech. And the SSL model mostly work on like 16 hertz sampling rate. How do you like handle this inconsistency between music and speech?
Yeah, it's a very good point. But frankly speaking, we only test the 16K hertz for our experiment. So we actually do not testing in that scenario yet. And I will say mostly because of the current data, like in the sending voice, is quite small in general. So making us like a little bit difficult to make a more like extendable like extension for that in the case of considering more like diverse scenario. Like so even for us, like when we're testing, for example, for the CMOS evaluation, we found that existing model, if you remember, like actually test on different like sampling rate for the CMOS, but actually the sampling rate for different system is actually not matter so much for the most activity. And there are so many reasons, but one of the things is that because we assume that because like the current issue is that still the quality of the sending voice synthesizer is not reached that bar that we started to care about sampling rate, or like higher, like or like more subtle changes in the middle. So that because of the range bias issue in the MOS evaluation, in general subjective evaluation, so this kind of subtle inference is still not discoverable, or like more like in the case of the data distribution. So as a result, the sampling rate is not that a big issue still, I would say, in the current stage, but maybe it will be after we have more techniques and more data coming up in the later space, this problem will be fixed more eventually. But at the current space, we do not care about so much of the sampling rate. Yeah.
And maybe one other question that I have is like we also like see that sometimes the semantic tokenizer have a better performance either in the speech, but one problem that we have is that they could lose information about a speaker's identity. Have you seen the same things in the singing voice domain here, or do you need to do add a specific trick like injecting a speaker embedding or something for that or not?
Yeah, it's a good point. Like when we extend into a multi-speaker, we also need to have the speaker embedding here. Like so we're actually mostly adopting the existing speaker embedding for sending voice as well, and it's actually working well. The reason is probably like actually in the Worksheet lab, actually there's also some sending voice inside it. Like it's not only the speech side, and where at the same time, like one thing that just to be additionally mentioned that most of the sending corpora here is in single singer for now, and because like the difficulty of collecting multi-singer data. There's actually some recently, for example, M4 singer and also the ACE singer that we proposed, like an ACE key thing we doing with our data curation. But actually, most of the widely used data with, for example, OpenCPUB is actually still in single singer. So that's the reality in sending voice because we really have limited data, and hopefully we could be mitigate this issue soon after we have more like emerged in the way of how we can handle this kind of procedure.
I see. Interesting. And maybe my last question is like we have seen in the speech that there is this tokenizer that combines semantic and acoustic. Is there anything similar also in the music domain, like Mimi or speech tokenizer, that try to combine the acoustic tokenizer versus the semantic ones? Or if you have a very paper, like
it's a good point. Like as far as I know, there's not so many works for now for the semantic representation to be involved. Mostly when they are having enough scope, they will be just shipped to the acoustic side. Where if they do not have that enough scope, for example, for our works, we only have limited data, so we're just going with the semantic. So it could be an interesting factor to be studied, but like not yet so far. Yeah, but thanks for the question. It's a good point. Yeah.
thank you.
Yeah, thank you so much.
Wade, you can ask your question.
Yeah, please.
Yeah, I was just wondering if there was something kind of that was unexpected to increase the performance of your experiments? Like you didn't expect that it would have such a large effect, but it turned out that it did.
That's a good point. Like I will say, like in terms of the exceptional things that we could be finding, is that first of all, it depends on the task that you're mentioning. You are mostly about the modeling side, or like the evaluation side, or the
Yeah.
data side.
The modeling side.
Yeah. In terms of the modeling, I would say like mostly the most of the result is like more like aligned with our expectation. But one thing that we want to briefly mention is, if you see, like we actually have different formulation here. It's like from the different models, different layers, and also the same layers from the same setup. And we actually find for the vocoder scenario, if we're going with only the single layer, but with more detailed information, we could be resynthesis as well, which is very surprisingly, I would say a little bit counterintuitive compared to the other one. So actually, probably for the audio resynthesis, if you want to use in this semantic representation, it's more to think about the subtle changes in the representation instead of from the more major changes from the different layers or from different models. So this is actually very interesting finding. And talking about that, one thing that I want to just briefly share with you is actually from a little bit another paper, but it's actually a similar story, is that when we're testing in the speech resynthesis, we found actually the semantic information from the self-reasoning model is actually not only semantic, they are actually have fluent many of the acoustic information inside. So if you ever try using the self-reasoning, directly using the self-reasoning representation for the resynthesis, you could be potentially find that actually it's very strong as a feature. But at the same time, even if you shrink the resolution, for example, making it 10 frames a second, so making like resolution to be 100 millisecond, the resynthesis quality will be still very good. So that means actually the semantic representation, the so-called semantic representation in the self-reasoning representation is actually contains lots of acoustic information, and actually enough acoustic information to be resynthesized away. So actually, that's why this is also like an insight that why we can continue with sending words from the semantic representation. Yeah, always like a good point. Yeah.
Yeah, very interesting. Thank you.
Yeah. Thanks for the question.
So if there is no other questions, thanks, Jiatong, for joining and presenting your work. It's very interesting. And we will upload the video and a slide on our website and our YouTube channel. For next week, we have Professor Shinji Wantabe from Carnegie Mellon University, and he's talking about open whisper style speech models, transparency, scalability, and advanced explainability. Thank you everyone for joining, and looking forward to meeting you all next week.